my pleasure to introduce Nicholas Fisher, who is currently supervising my postdoctoral work. And I'll be cheating a little bit to get stuff right. So Professor Fisher is actually one of the few distinguished professors we have here at SoMAS. He's also acting as a director of CIDER, which stands for Consortium for Interdisciplinary Environmental Research. And his research currently are in marine biogeochemistry with a specific focus on bioaccumulation of contaminants in aquatic biota and the geochemical, toxicological, and public health consequences of this bioaccumulation. Nick has received his PhD in 1974, actually here at Stony Brook University, but it's a Department of Ecology and Evolution. And since that time, he has made a few stopovers, firstly at Woods Hole, then he went all the way to Australia and to Europe and Monaco labs, and then he returned to New York and took a job eventually here at Stony Brook. And he has been mentoring PhD and master students since and continuing his interesting research. I think the research that is happening in the lab right now is very exciting. I'm happy to be also part of it, and hopefully you'll be able to enjoy it throughout today's presentation of Nick Fisher. So I'll let him take it over. Oh, yes, thanks.
Okay, well, greetings everybody. It's almost the second anniversary of the disaster in Japan that was a result of an earthquake, a very powerful earthquake off the coast of Japan, which resulted in a massive tsunami which hit the northeast section of Honshu Island. And on that, pretty much at the spot where the tsunami hit, there's a very large nuclear reactor at the location called Fukushima Daiichi. And this is a story of the aftermath of that, of the impact of that tsunami, and it was full of surprises for us. So I'm going to proceed straight ahead. Everything I'm going to tell you about, by the way, in a sense, I'm a spokesperson for a group. And the group most prominently includes Zofia Baumann, who introduced me, and Daniel Madigan, who is finishing up his doctorate at Stanford University. So they all had tremendous input on the data generation and interpretation. So Fukushima is located right there on the main island of Japan. The tsunami basically disabled the nuclear installation. There were explosions from hydrogen gas. There was a lot of release of radioactivity, both in into the air and directly into the water. The date of the tsunami was March 11th, I believe, but the date of maximal release of radioactivity into the Pacific was estimated to be April 6th, so about 3 or 4 weeks afterwards. And there was immediately a 30-kilometer radius that was drawn. People were not allowed to go anywhere near it, and food could not be collected from there. This is largely an agricultural area, as well as an intensively fished area off the coast. If you look at the radioisotopes that were released from Fukushima, the dominant isotopes were iodine-131 and cesium-137 and cesium-134. And I'll be talking mostly today about the two cesium isotopes. So let me start a little bit with the cesium. So background levels of cesium in the Pacific were not zero. The half-life of cesium-137 is 30 years, and a lot of that cesium that is present, cesium-137 does not exist naturally in seawater, but a lot of the cesium-137 that was present as background is a result of basically a legacy of fallout from nuclear weapons testing, which peaked in the early to mid-1960s. It continued beyond that, but it peaked in the about 63 or 64. So there was a background level of cesium-137 that was present in biota and in surface seawater of the Pacific. That's clearly detectable, but at very low levels in current times. Then in 1986, Chernobyl event occurred, and there was a big release of cesium-137 globally. Most of it fell closer to Europe, in Northern Europe, and also the Mediterranean and Black Sea. Chernobyl, as you will recall, is in the Ukraine. So there was a spike of cesium-137 that was introduced even into the Pacific. And note this is a log scale, but following Fukushima, an incredible release of cesium-137 into the Pacific. In fact, it's the largest single accidental release of radioactivity into any body of water in the world. Now, we participated in a cruise that was put together in a hurry by myself, but most particularly by Ken Bissler at the Woods Hole Oceanographic Institution, who was able to find some private funding to address the aftermath of the Fukushima disaster. We had two scientists from SoMAS who participated, Hannes Baumann and Jenny George, who's no longer here, but she was a student with Chris Goldberg. And Chris certainly helped out a lot in planning for this as well. And we collected, they collected zooplankton and whatever fish they could get, and they only at a few stations were fish collected, small myctophid fish, a couple of inches long, that's it. And collected in nets, and they were analyzed for whatever gamma-emitting radioisotopes we could detect. Turned out that there were only three that we could detect: cesium-134, cesium-137, and silver-110M. So the samples were collected off the cruise. It was a 3 or 4 week cruise off Japan. The samples were frozen and shipped to Stony, Brook, where they were analyzed for radioactivity. The cruise plan went as far off as 600 kilometers off the coast of Japan and as close as 30 kilometers off the coast. We were not allowed to get closer than 30 kilometers. This depicts the Kuroshio Current, which heads basically northeast from Japan. And the Kuroshio acted essentially as a pretty effective barrier, it turns out, for the waterborne cesium. So we would see generally higher levels of cesium, and these were analyses done by Bissler and his colleagues at Woods Hole, higher levels of cesium north of the Kuroshio than within the Kuroshio or south of the Kuroshio. And the two main isotopes, or the two main elements that had radioactive isotopes that were present were iodine and cesium. Now, note that cesium is in the same column of the periodic table as potassium and sodium. Okay. And it turns out that cesium is a non-essential element for living organisms, but it's taken into living organisms through a potassium uptake channel. And it goes where potassium goes in organisms, both unicellular organisms and very large organisms as well. And in very large organisms, it typically is found or sequestered in the muscle tissue of fish, for example. Iodine is not very biologically active for most organisms in the ocean, except for brown macroalgae. seaweeds, which can concentrate it about 10,000-fold out of seawater. But generally, iodine is not particularly highly concentrated in marine animals. The main point about the iodine for today's discussion is the short half-life. It's 8 days. So after 70 days, which was about the point at which our cruise took off, there was only about 1/10% of the radioactive iodine remaining. And after 1 year, it's an incredibly small fraction of 1% of the iodine remaining. So essentially, the iodine decays very quickly. So in terms of finding its, tracing it, finding its presence in the ocean, whether it's in the water or the biota, it's extremely difficult to do even after about a month or so. It's also worth recalling that there's a lot of stable iodine in seawater, and it's present at concentrations in surface waters of about 400 nanomolar. And as I noted before, it's concentrated by brown macroalgae. It's an active uptake, so they actively take it up. And it's concentrated on the order 10 to the 4 out of seawater. So it's enriched 10,000-fold greater than surrounding seawater. But generally, very little bioaccumulation of iodine in most other marine organisms. Sorry. Cesium, so there's 2 isotopes I'm going to be talking about today, and for a reason. Both of these, Cesium 137 and 134, were released at almost perfect 1-to-1 ratio from Fukushima. So, and it's important, as you'll see, that we're going to be focusing on the ratios of the 2 isotopes. Cesium 137 is the one that has the 30-year half-life, so that's the one that's still detectable as a result of weapons testing in the 60s. It's a fission product from the splitting of uranium. Cesium 134 has a 2.1-year half-life, so it decays much more quickly, of course. It was undetectable in Pacific water and biota off Japan or anywhere, actually, in the Pacific just prior to the Fukushima disaster. And cesium is also very abundant in seawater. Stable cesium is very abundant in seawater. And it's present at concentrations of about 40 nanomolar in seawater, and it behaves pretty conservatively in seawater. Cesium, unlike iodine, which has some biological function in living organisms, cesium has no known biological function, at least none that I'm aware of, but it generally follows potassium uptake pathways in organisms, as well as tissue distributions. It shows very low uptake in marine phytoplankton at the base of the food chain with concentration factors under 100, and in fact not significantly different from 0, at least in experiments we've conducted. But it's much higher, its concentration factors in freshwater phytoplankton are considerably higher, on the order of 10,000, because there's no competing or very little competing sodium and potassium in freshwater, unlike in seawater. So one sees in the Great Lakes, for example, a lot of cesium associated with phytoplankton, but in marine phytoplankton, it's virtually undetectable. It also displays modest biomagnification in marine food chains. It's really one of the only metals that does show biomagnification in marine food chains. Generally, metals, and by biomagnification, I mean the concentration is higher in the tissues of the predator than in the prey. And methylmercury, mercury in the form of the methylated form, methylmercury is biomagnified considerably in marine food chains and is certainly a public health concern. But most metals that people care about, they worry about, chromium, cadmium, lead, and so on and so forth, show virtually no biomagnification. In fact, none. Cesium shows very modest biomagnification, so it increases, or has been seen, at least in the past, to increase a little bit as you go up the food chain, but not dramatically, not as much as methylmercury. It also has very high assimilation efficiencies in fish. So when a fish eats some prey item, let's say a smaller fish, it will, the predator will assimilate 70 out of 100 of the cesium atoms it ingests. And by assimilate, I mean it crosses the gut lining and actually enters into the tissue of the fish, usually muscle tissue. It's also taken up from from the aqueous phase in water. Unlike most of these metals, cesium is accumulated from the aqueous phase as well in marine fish, and it's important to recall that marine fish drink water for osmotic purposes, so there might be a drinking uptake pathway for cesium. Okay, once the samples were received at Stony Brook, they were freeze-dried and pulverized to a homogeneous powder. They were weighed, of course, and they were put in detectors that are sort of hidden inside these crypts of solid lead. And the detectors were broad energy, high purity germanium detectors that enabled us to distinguish many different isotopes simultaneously. And what we found is we found those two cesium isotopes and the isotope of radioactive silver, and we saw nothing else in any samples. But we were able to quantify with this gamma spectrometry how much of each isotope was present in each sample. Okay, so Bissler's data for cesium in surface waters is denoted here, and this is some 600 kilometers off the shore of Japan, as close as 30 kilometers. And generally, the closer to the shore, the higher the cesium concentration in the water. Hardly a surprise, but it was clearly detectable in virtually every sample, even as far away as 600 kilometers. This was in mid-June of 2011, so about 2.5 months after the release. We also measured, so this was done in our shop, cesium 137 and 134. I'm only showing the 134 in Biota, and silver 110M in Biota. And the cesium, both 134 and 137, were found in every single sample of fish and zooplankton, and we characterize the zooplankton as copepods, euphausids, jellyfish as well. Mostly copepod samples, but some euphausids as well. Silver 110 was present in all of those samples, but not present in any of the fish. Now, that's interesting. We know that silver displays very low assimilation, at least in experiments, very low assimilation in fish, and it may be that whatever silver they have ingested from their diet, they just defecated and it was not detectable in the fish. But we saw no silver in fish at any time. Here, the data summarized, so 17 different samples of copepods, and these are composite samples, and mean concentrations of cesium-137 and units of becquerels per kilogram dry weight. A becquerel is a measure of radioactivity equals 1 disintegration per second. Those of you who are familiar with microcuries, 1 microcurie is 37,000 becquerels. So we averaged about 15 becquerels of 137, about 18 of 134, and about 8 of silver. And note the potassium-40, about 200. Now, potassium-40, we also measured in all samples. That's naturally occurring. So potassium-40 is one of the primordial radionuclides with a half-life close to 2 billion years, I believe. And so this was present during the formation of the Earth. It was present before any nuclear program. Nuclear programs do not enhance the presence of potassium-40 in soils or the oceans. Potassium-40 accounts for about 90% of the naturally occurring radioactivity in surface seawater. And because it's potassium, which is an essential element, is in fact concentrated out of seawater by marine organisms. So you see potassium-40 in all living organisms, including us. So each of us is radioactive right now, primarily from potassium-40 and a little bit from carbon-14, which is mostly cosmogenic, but not all. But the potassium-40 is all natural, and most of the carbon-14 is natural. And so you're each giving your neighbors a dose of radioactivity right now. Of course, they're reciprocating. And so all living things have evolved on a radioactive planet, and it's worth bearing that in mind when evaluating the risks associated with these fairly low concentrations of cesium that were detected in plankton. This is copepods, large zooplankton, and the fish. The concentration factors in copepods of about 70 or 80 were pretty close to what was estimated by the International Atomic Energy Agency in their compilation about 10 years ago. The concentration of 134 to 137 in our data, this was a paper that came out last year in PNAS, and pretty much matched the one-to-one line. The solid line is the hypothetical one-to-one line. It's worth noting as well that the natural radioactivity, primarily potassium-40, and now I'm just talking about gamma emitters, the natural radioactivity of potassium-40 was considerably higher than the total anthropogenic radioactivity in Biota off Japan, and a ratio of about 6 to 1. And prior to the Fukushima accident, the concentration of cesium-137 was, let's say, about 40 to 80 millibecquerels. And notice here the values are about 50 becquerels. So it went up tremendously following Fukushima. Okay, so this is the star of the show. These are bluefin tuna. I'm being forced to learn something about fish these days. For me, fish tastes good with the tarragon butter sauce, but other than that, I don't know. But it turns out bluefin tuna are the most valuable fish on Earth. One recently fetched over $1 million in the Tokyo market this year. They can live to 20 to 30 years, I believe. They can get to over 1,000 pounds. They're amazing machines. They must keep swimming, and they swim at very high rates, and they're voracious eaters. They have been recently recognized, the Atlantic bluefin tuna is long recognized now, and the Mediterranean bluefin as an endangered species. The Pacific bluefin has just, I think, a week or two ago been recognized as a fishery that's in serious trouble. So until 2 weeks ago, it was not considered endangered, and it's fast being recognized that it's being heavily overfished. So there's a lot of interest in the Pacific bluefin tuna from a conservation perspective. It's also of concern from a public health perspective in that it's been recognized to concentrate methylmercury to very high levels. It's sort of outside the focus of today's talk, but it's worth reminding ourselves that in considering toxic substances in our seafood, we can't look at them just by themselves, but we have to compare them to other things that might be co-occurring in that same fish. So there could be persistent organic pollutants, for example, but in particular for tuna, mercury is the story. And in fact, there are seafood advisories throughout the United States about fish consumption due to high mercury levels, especially with big tuna, swordfish, shark, things like that. Okay, now, I was educated by Dan Madigan, who told me that bluefin tuna actually, in the Pacific, spawn in waters of the Western Pacific, off Japan, off the Philippines. And then when they're either about 1 year old or about 2 years old, they decide that they're going to swim across the Pacific Ocean, and they reach North America, and they go into the California current off California and Mexico. and they get very large there. And at some point, years later, they swim back to Japan, or waters in the Western Pacific, and spawn. And they may make this round trip more than once. So I'll go back to this slide in a minute, but I just wanted to give you this overall sort of bird's eye view. So we collected 15 bluefin tuna in August of 2012 off San Diego, not expecting to see anything, frankly. And Dan called me and said, "You think it's worth looking at?" And I said, "Probably not, but we'll take a look. I'll humor you." So we collected the bluefin from sports fishermen off San Diego, and then processed the samples in the same way as the plankton samples. So they were freeze-dried and weighed and analyzed with the same gamma detector. And analyses took up to 5 days per sample to get statistically meaningful counts. And what we found, and we were quite surprised, was that we found Cesium-134 and Cesium-137 present in all of the Pacific bluefin tuna, N equals 15, that were recent migrants. And we knew that they were recent migrants by their size. So bluefin of that size had to have arrived from the Western Pacific. And the bluefin are highly migratory species. And unlike yellowfin tuna on the bottom 3 rows here, yellowfin tuna are residential fish. And so by residential, I mean they don't swim across the Pacific. So the yellowfin that are found off California are basically stick to the eastern Pacific. The yellowfin around Japan stick to the western Pacific. And we saw no Cesium-134 in the yellowfin, and background, in quotes, levels of 137, Cesium-137 in the yellowfin, about 1 becquerel per kilogram. So that's the level of radioactivity that we see as a legacy of the nuclear weapons testing. We also saw those same values in Pacific bluefin tuna that were frozen in Dan's lab. And these were collected in 2008. Again, no 134 and background levels of 137. But look at the cesium levels in the bluefin in 2011, after the Fukushima accident, clearly detectable levels of 134 and 137. And also look at the mean potassium values. Okay, so the mean potassium values were about 37 times higher than the total 134 and 137. So again, the natural radioactivity is far greater than the artificial radioactivity in the bluefin by the time they got to California.
Okay.
Yes.
I forget what the energies are of the different gammas. What are the energies of K40 versus the cesium?
K40 is,
1461.
what was it?
1461.
Yeah, 1461 kV, and cesium are in the 600, high 600. Okay. We also looked at the cesium ratios of 134 to 137, and by the time they got to California, the ratios were about 0.7, 0.6. So again, the Cesium-134 was, clear, unequivocal evidence that these fish picked up the cesium. These new migrants picked up the cesium in their youth, off in waters off Japan, and then swam across the Pacific. Now, bear in mind that these were collected in August of 2011, and the date of maximum release from Fukushima was only 4 months earlier, in April 6th, or 4.5 months. So they would have had to have accumulated whatever cesium they were going to pick up prior to transport across the Pacific. Okay, so another look at this slide. So essentially what's happening is that they're picking up 134 and 137 from the seawater, the contaminated seawater near Japan. As they swim across, they're getting a little bit larger, so there's some growth dilution because they're not picking up any new cesium-134 during their migration. So whatever 134 was in their tissues is getting diluted by new organic materials that just get bigger and heavier. In addition, they are excreting 134 and 137. They excrete cesium at a rate of, we estimate, about 2% per day. And so it's not irreversibly down to the fish. They're also picking up low levels of 137, which was the legacy from the weapons testing. So and again, the 137 has a longer half-life than the 134. So by the time they got to California, they had ratios of about 0.66 of 134 to 137. But in waters off Japan, their ratio was 1 to 1. And then the yellowfin tuna just swim around here, so they're not picking up any cesium off waters off Japan. Right? Yes.
In bluefin it's 1 to 1, or just in other things it's 1 to 1?
In both, in bluefin and other fish. The Japanese have reported levels, yes. Okay, so then we tried to calculate, this is rough and ready, okay, but we tried to estimate what the concentrations were during their transport across the Pacific. So at the time, this was on the x-axis, we see time before capture in California in days. So 0 means this is at the time. This is the time that they would capture, and these are mean values. And so the total cesium concentration was about 10 becquerels per kilogram, and you see values for 134 and 137. Okay, here. Then these are the individual fish, the 15 individual fish that we measured, corrected for background, where we looked at the ratio of 134 to 137. Now we know that the 134 to 137 was released at a ratio of 1 to 1 in Japan. And the fish and all other biota that we looked at, mostly plankton, had a ratio of 1 to 1 in waters of Japan shortly after the accident. So when would the ratio have been 1 to 1? And we knew that we estimated the release rate was 2% per day. We know that the decay rate constants for the two isotopes. So we estimated that about 4 months or 120 days prior to capture, their cesium-134 to 137 ratios were about 1 to 1, which meant that, if that's true, that meant that these fish had only about a couple of weeks to maybe a month to pick up the cesium before migrating across the Pacific. And it also means that the cesium concentrations in waters off Japan were much higher. In fact, they were 15 times, we estimated them to be 15 times higher than what they were when they were caught in California. And we compared these values to unpublished values that the Japanese present online, and they still present them online. And these values were spot on to what the Japanese reported in their waters. They have not undergone any peer-reviewed publication, the Japanese data, so but the match is pretty close. I should also point out that the Japan safety limit currently is 100 becquerels per kilogram wet weight, or about 400 becquerels per kilogram dry weight. So these values are well below safety limits in Japan, and even further below safety limits in the U.S., which has different safety limits. We were curious to see whether there was a relationship between fish length and cesium. At least in 2011, we did not see any relationship for either of the two isotopes, at least nothing significant. Well, we published this in PNAS, and immediately there was a firestorm of attention. My God, radioactivity in our seafood. And it was carried in 700 newspapers in the US, at least 400 overseas. Every TV station, radio, you name it. I've never been approached by Al Jazeera TV. That was a first one. And every newspaper covered it, except the only one I read, which was the New York Times. They chose not to comment on it at all. But every other one covered it, often on the front page, and got a lot of attention. And why does it get this attention? Well, and of course, the inevitable cartoons came out. And, on the one hand, you can say, this was from Boston Globe, so you can say, yes, we should be rightly concerned about the radioactivity. But 20,000 people lost their lives in one day from this tsunami. About 17,000 were killed outright, and another close to 3,000 are missing, presumed dead. So about 20,000 people were killed outright. You heard about that for maybe 2 days on the news, and then never again. But for 2 years now, you're constantly hearing about the dangers of the radioactivity from Fukushima. So there's an imbalance there, and it was a major tragedy in Japan, as you can well imagine. Can you imagine 20,000 people being killed outright, Long Island or California or anywhere else, by drowning? It was really horrible. So, those of us of a certain age, mid-30s, remember a time when the nuclear scare was everywhere. And there was nuclear weapons testing, which was genuinely terrifying. People were building fallout shelters everywhere in the US, including in New York. And immediately, of course, there was a plethora of wonderful science fiction movies that some of us remember, giant ants or giant gorillas or giant moths or you name it. And this is what people kind of grew up with. This is what I grew up with. And there was this sense that radioactivity is the most dangerous, terrifying, horrible thing that could possibly befall any living creature. So there was a lot of, and we're still living, I believe, with this legacy from the Cold War of fear about radioactivity. And in a way, it's very understandable. And high levels of radioactivity are genuinely dangerous, of course. But most of the radioactivity that we're exposed to, even through the marine food chains from Fukushima, you'll see are very low compared to levels that can actually cause any impact on us. Sorry. One other thing I just wanted to bring to your attention, that if you look at the history of radioactivity in the oceans, right, you see the amount that was dumped either intentionally or accidentally globally. It's about 1% of the radioactivity that was released in nuclear tests. And the amount released totally by human activity accounts for only about 1% of the total radioactivity in the oceans. So 99% of the activity in the oceans is natural. And it has always been. And it's mostly potassium-40. So what are the risks to humans? Everyone wants to know, is it safe to eat, a tuna sandwich, right? So the relative risk of cancer above natural incidence of the disease is about 4 to 5% per sievert. I'll explain what a sievert is in a minute. And one sees statistically significant elevations in cancer risk at doses greater than 1 to 200 millisieverts. So what's the dose we get from eating Fukushima tuna? So the doses, a sievert, by the way, equals 100 rems, which equals 1 joule of ionizing radiation absorbed per kilogram of tissue. I won't go into the details of that. But this is well worked out by the International Commission of Radiological Protection. So if you eat, let's say, 200 grams of tuna from Fukushima caught in California, and we're now only considering 134 and 137 cesium, because we didn't see any other isotopes. The dose that you would get is 0.008 microsieverts. The dose that you would get from the potassium 40 in the same piece of tuna that you're eating would be 0.1 microsievert, still very low. The dose you would get from eating a banana, for example, or Brazil nuts, or any potassium-rich food that we never think twice about, would be about the same as the potassium 40 from the tuna, and far higher than from the cesium in Fukushima. The dose you would get from a dental x-ray, put it in perspective, is about 5 microsieverts, and a one-way flight from New York to Los Angeles, for example, from cosmic rays, about 40 microsieverts. Certainly, medical interventions, CAT scans, x-rays, and so on and so forth, you're also exposed to radioactivity. There are a lot of things that we're natural, or that we're routinely exposed to in our daily lives. Now, if you consider people who like to eat a lot of seafood, so top 5% of recreational fishermen in California, and we used data that were available for how much different groups of people eat in different areas, and they would acquire about 5 microsieverts per year. All right? From cesium, about 62 from the potassium in the tuna, which equals about 47 bananas per year. So the banana unit here. And then if you look at the average seafood consumer in the US, it would be about 1, which equals about 9 bananas per year. In Japan, what about in Japan? Well, people eat more seafood in Japan, and the radioactivity in the fish in Japan was about 15 times higher than it was in California. So the dose they would get would be about 33 microsieverts as opposed to 0.008. But still equal to about 1 banana per day. So avid seafood eaters would get doses, turns out, about 5 or more than 5 orders of magnitude lower than the minimum levels leading to cancer. 5 orders of magnitude. Remember, like 2 orders of magnitude is big. That's like the difference between your walking speed and a jet plane flying overhead. 5 orders of magnitude. That's a big difference, right? And so these, because we can detect it, doesn't necessarily mean it's going to pose a problem. Here is, we also we're concerned about the doses to the organisms themselves, the marine organisms. And this, again, these were rather complex calculations. But the bottom line is that the zooplankton near Japan, tuna near California, and tuna near Japan, the doses, they don't use sieverts, they use grays for all organisms other than human beings. I could explain the rationale after the talk if anyone's interested. And these, again, these levels, a gray is the absorption of 1 joule of ionizing radiation per kilogram of tissue. And note that we have potassium 40, which has quite a bit more, provides a bigger dose than the cesium, but especially polonium-210. Now, polonium-210 is also a naturally occurring radioisotope, which derives from the decay, ultimately, of uranium-238. And it decays, it has a 4-month half-life approximately, and it decays to stable lead. And polonium-210 is an alpha emitter. And alpha emitters cause much greater biological damage than do gamma emitters. And there's a lot of polonium that's in seawater from the decay of uranium, and it's bioconcentrated very appreciably out of seawater by all kinds of marine organisms, particularly shrimp, as it turns out. So you get a very big dose of radioactivity if you eat shrimp. And we do assimilate polonium out of seawater. I mean, sorry, we do out of our food, and marine organisms assimilate polonium out of their food as well. Polonium is bioconcentrated in phytoplankton. It enters into the cytoplasm of the phytoplankton and it gets passed up the food chain. So the biggest radiation dose that marine organisms experience is that from polonium. And the biggest radiation dose we get from eating seafood is from polonium. Dan was wondering, well, with all these tuna swimming across the Pacific, how much total cesium is being transported from the Western Pacific to the Eastern Pacific in California? Let's say they all lost it right away. And so we looked at average catches in tons per year from 2000 to 2010. We assumed that all the cesium was in the mussel. We calculated the mussel biomass. We took average values, and we calculated that in 2011, about 4 million becquerels was transported across the Pacific, which sounds like a lot, but that's about equal to 1 millicurie. And those of us who work with radioactivity know, and I order millicuries of radioactivity all the time from my lab, and anyone who works with radioactivity does as well. So a millicurie is not a lot of radioactivity. We also think that we can use these radioisotopes that were released from Fukushima to trace migratory patterns and even the timing of migration by looking at the ratios of the two cesium isotopes for looking at tracing animals that are known to be migratory, but their routes of migration are sometimes not very well worked out. These would include shearwater birds, loggerhead turtles, possibly the giant bluefin tuna that go down to New Zealand, salmon sharks, which are thought to migrate between Japan and Alaska, not sure, and possibly other tuna species such as albacore, and some salmon. So we think that isotopes released from Fukushima can be used to trace migration patterns as well as other animals. So some of our questions of how to move forward this year in 2012 or last year in 2012 and now in 2013. So what proportion of the older, larger fish in the California current system are residents, and what proportion are new migrants from Japan? And do New Zealand Pacific bluefin tuna make round trips to Japanese waters? Apparently not known at all. Okay. So I would remind you that our 2011 data were from fish that spent maybe a month in contaminated waters. So in 2012, they had a year to mature in contaminated waters around Japan before crossing the Pacific. So it's plausible, perhaps, that the concentrations would have been higher in 2012 than in 2011. Alternatively, the cesium isotopes may have been dissipated and dispersed through ocean currents and whatnot. So the concentrations in the water would certainly be lower, and so the fish may have been exposed to much lower concentrations. So we did not know. So we collected actually a few hundred fish, and we've started doing those analyses. And here's what we found. And this is a paper that came out last week in Environmental Science and Technology. And these first two bars, the open bar is 134, and the solid bar is cesium-137. That's from 2011. Those were the new migrants. These are the migrants in 2012, 28 fish analyzed so far. Significantly lower than last year, which is not a surprise. I mean, it's kind of comforting to know. Cesium-134 was clearly detectable. It was unequivocal evidence that these fish packaged the cesium in waters off Japan and swim it across. So significant differences at 0.01 level of significance for those who care about such things. And then we also compared the larger migrants. So there were some fish caught in California that were larger, and we assumed from their size that they were more than 1.7 years old. And we only had 5 of those, and they were clearly migrants because they had Cesium-134 present. Then we compared them with other larger bluefin tuna that were present in California. We had 17 of those, again, older than 1.7 years, and they had no 134 and background levels of 137. That's weapons fallout levels of 137. So these guys had been sitting around or swimming around in California waters for the last year. These ones were new migrants from Japan. And again, yellowfin, background levels of 137 and 0 of 134, consistent with last year. So levels on average were about, they were less than half in 2012 from what they were in 2011. So they're clearly going down. And this is another way of showing the data that I just alluded to. So these are the 134 to 137 ratios in migrants versus in residents. So in the residents, it would be 0 because there's no Cesium-134 present. And out of curiosity, we were wondering, well, how fast do they have to swim? By using our radioisotope data, and we found some evidence that they can swim even faster than 4 months. So we calculated what the swimming speeds were, and we know that they're actually consistent within the range of values using electronic tags. They can go, these fish swim about 200 kilometers per day. Pretty fast. That amounts to an average of about 5 miles per hour across the Pacific without stopping. That impressed me. This is recently caught bluefin. This one's, I think, about 80 kilograms. And so I do want to emphasize this is a work in progress. But 134 and 137 cesium do accumulate in bluefin tuna in waters off Japan. And they're retained for a long enough period to be transported across into California waters. Yellowfin tuna, which are residential, show no evidence of Fukushima radioactivity, meaning that there's no cesium present in the water or in the prey in California waters, at least not yet, that would be accumulatable in resident predators in California. Radioactivity was clearly detectable in tuna in California coastal waters, but at very low concentrations compared to natural radioactivity. And doses both to marine biota and to human consumers are low, and I dare say not worth worrying about, at least in the animals that make it across the Pacific. There are some fish that, not tuna, but there are some fish, especially freshwater fish and some benthic fish, that have been reported by the Japanese to have extremely high levels. These are coastal, very close, hugging the Fukushima coast. So there are certainly fish there that exceed anybody's safety limit, but they are not representative of fish far offshore, certainly not representative of fish that get to California. And we believe that the cesium isotopes may be useful in tracing migration of tuna and other species of fish and other large migratory animals. And I think that's the end of the story. Yes, and so I want to especially thank Zofia and Dan Madigan for their tremendous efforts. And Ken Bissler was a great colleague at Woods Hole, and Sheila and Jenny George and Hannes Baumann for their sampling last June. And thank you very much for your attention.
the slipping factor.
Yes,
But
I forgot about that.
Yeah. This is a question about cesium. So, two questions. Number one, have analyses been done in different parts of the body of a tuna for cesium? And the second question is, let's forget about cesium as a radioactive. Does it have any, since it's going through, I assume, potassium channels?
Yes.
Has anybody ever done experiments to see whether cesium has any effects on potassium, the various potassium channels that are known?
Okay. When people have analyzed tissues of fish, marine fish, they find it's heavily concentrated in muscle tissue, which unfortunately is the part of the fish most people eat.
Right, it's where you would expect it to be with the world of potassium channels are.
And that's where it is. In terms of interference with potassium uptake, I have not seen a study on that, but I would seriously doubt it because the potassium, the abundance of potassium is so much greater than that of cesium. And bear in mind that most of the cesium that these fish are seeing, even in waters off Japan, is stable cesium. So these radioactive, that's why I showed the cesium concentrations at the very beginning. So most of the cesium that these fish see, they can't discriminate between radioactive and stable cesium. So most of the cesium that they're seeing, they've always seen, is stable cesium.
Is it ionic?
Yes.
Is it well, then it is charged, so it has some chemical, I mean, it may be that it has the same chemical activity as potassium and really has no different response, but it could be different. I wonder.
It could be. I mean, I can't rule it out because at least I have not done those studies. I'm not aware of anyone who has, but I would think it's unlikely. Mary.
So one of the problems from a geochemistry point of view about these kind of accidents is that they're transient. Okay. So how long are you going to be able to see this?
Yeah, so that's a real good question. So we think we can use the cesium-134 probably for another 2 years, I'm guessing. And for the 137, which is much more, much elevated beyond weapon stuff, that'll be available for decades.
But you can't do the ratio.
We cannot do the ratios. That's right. Glenn.
This is a tangential question, but the one isotope that does concentrate that you mentioned, at least in something as iodine, which is going into seaweeds that are eaten in large amounts in Japan. What can you say about that?
Right, so the question was, what about the iodine that's concentrated in seaweeds which are eaten in Japan? Is this a concern? The Japanese were concerned about it. It turns out, by good fortune, most of the Japanese, as I understand it, most of the seaweeds that are harvested for human consumption were from a different area of Japan. So, and they did analyze the iodine present there. It was present, but not at very high levels. Where it was detectable, they didn't harvest it. The nice thing is you can wait a couple of months and it's gone. That's it. All right.
Two quick questions. Really a great story. If this data is available, in the beginning, from the early nuclear explosions, were comparable type studies done either in fish or in the air, just in terms of asking the same sort of questions?
They were, yes and no. So there was some really excellent work done, mostly by West Coast scientists in the U.S., analyzing radioactivity following weapons testing in Inuitak and Bikini. And they found radioactivity in bluefin and other species of tuna, as well as other marine animals. But they didn't use it to trace migratory patterns. I guess didn't occur to them, or I don't know. But they clearly recognized it. The levels were much higher there, much higher. But nevertheless, it was more aimed at, is this something that we need to worry about eating?
The other hand, with the K40, or with potassium in general, in mammals, which is the level we work at, it's concentrated 20-fold intracellular. Is it similar in fish? It's mainly intracellular, by a factor of 20 over extracellular? And if so, and you're measuring the combination?
I think that's right, yes. It would be intracellular, that's right.
Nick, could you do the same calculation in your young 2012 migrants to figure out what kind of concentrations they might have been exposed to look at what, you know, what the situation was a year later? Did it match up with what they were measuring in the water?
I can answer.
Yeah, please.
I'm sorry. So it turns out that the Japanese stopped really reporting the values for Pacific bluefin tunas later on. I think that they may have reported maybe one fish 2 months later. And we, however, did not back calculate how much cesium would have been there in these fish prior to their migration. The levels in Japan were about 20 or 25 becquerels per kilogram on what they think. So it went down quite a bit, or stayed similar to what the year before concentrations were, but only one fish available.
Yeah, but it seemed your first calculations were predicting back to water levels, right?
No.
2011?
No. So the 2011 data, what we did was we calculated what the fish would have had
Yeah.
when they first left Japanese waters.
Oh,
And those concentrations were about 15 times higher than they were by the time they got to San Diego. But, and they were pretty close matches to what the Japanese independently measured in the few bluefin that they reported on in 2011. Okay. So that gave us some confidence that we were not like crazy. Well, you know. I haven't seen, and there are reports that the levels in marine fish off Japan have not declined very much in coastal waters off Japan in the last year. But we did see an appreciable decline, at least in the bluefin tuna that got to California. It didn't go down like an order of magnitude or anything, but I would say it's less than half.
Is there still material leaking? Is that why?
Yes. Well, that's not known, but it is strongly suspected that there's a lot that's still leaking. And as well, every time there's a big rainfall in Japan, there's a lot of cesium that fell on the land that gets washed out to sea by rivers. So the rivers are heavily contaminated with cesium, and the soils are heavily contaminated with cesium. And so that stuff is a continuous release into coastal waters. But what people are most concerned about is continuous leakage from the nuclear plants. And there seems to be pretty good evidence that that's occurring. It's nowhere near what it was in 2011, but it's not zero. Any other questions? Yes?
I just have one question. So you said that the fish might find way back to Japan and spend some time and then come again. So do you know, do you have an idea how many times in their lifetime they can do that? And if they went back and spent another couple of months in those waters, if it's still leaking from the land and they pick it up by accumulate and then come back, so would those levels be as high?
We don't know what those levels would be. So, first of all, I don't know how many round trips bluefin make. Maybe a fisheries biologist here knows, but I know that they're known to do it at least twice. Certainly, if they do go back to waters that are contaminated, then they can pick up additional cesium, which again won't be irreversibly bad to their tissue, but they'll pick it up. Yeah, but the other interesting point I should have made, and that is that these tags, these, in a sense, chemical or radioactive tags in the fish basically provide a retrospective view of where the fish had been. The electronic tags that are being used by fisheries organizations and fisheries biologists tell you where the fish is going to go from the moment that you tag it onward, in the future. They are much more expensive, I believe. They can be like $1,000 a tag, and you rarely get them all back. So this does not displace the electronic tagging, which is also provides really very valuable information, but it provides a different kind of information that can supplement and complement the electronic tagging approach.
Thank you very much, Nick, and I'll have to say we're not having tuna fish for lunch. There is need if anyone would like to continue talking